Hinton for his fundamental, very much mathematical contributions to machine learning. So we see that artificial intelligence is having a very strong influence, not only in society, in industry, in technology, but also on science, both on the daily science we all do with our personal computer, but also to the most ambitious projects of science. So in this context, as mathematicians we are, from the perspective of traditional applied mathematics we all work on, how do we define applied mathematics? What is applied mathematics? Well, applied mathematics, as you know, this is a concept, a field that was, the contours of this field emerged after the Second World War. So it's more or less the merging, the fusion of traditional mechanics that leads to models like ordinary differential equations and partial differential equations that, to be understood, require of the modern theory of partial differential equations, which is very much rooted on the classical developments by Fourier, Gauss, and so on, but very much also on modern functional analysis that was essentially developed on the first half of the 20th century, like distribution theory, Hilbert spaces, Banach spaces, Sobolev spaces, harmonic analysis, and so on. To this, of course, we have to add numerical analysis and scientific computing that both from a theoretical perspective, concepts and, tools such as finite element methods, for instance, together with scientific computing that was very much developed thanks to the acceleration of the computer power. And then, of course, there are other side topics that are, of course, extremely relevant also in applied math. I mean, you have ideas coming from probabilities and stochastics. I think that will be one of the topics that Professor Zhou Zenan will lecture on in his lectures. There are wavelets coming from Fourier analysis, maybe inverse problems, of course, optimization, control. These are central topics always in the development of an applied topic, any applied project. So this is more or less what applied mathematics is, right? And until now, artificial intelligence was something else. Was a field that was being developed maybe in the community of computer science that most of us as applied mathematicians we were not aware of, right? And now that, the field is here and with such a ubiquitous presence in our lives and in our university activities, is somehow time to build a bridge, right? And the goal of these lectures is to precisely offer you my own perspective from my own small corner on how these bridges can be built. And this is also an invitation for you to try to do it, because there is not only one bridge from applied mathematics to artificial intelligence, there are many bridges. It very much depends on what is the topic you work on your own perspective. You are a probabilist, if you are an analyst, if you are a numerical analyst, if you are a computer science, probably the bridge that links you with artificial intelligence is not the same. You can build your own, right? But there is certainly a lot to be done. And this is an activity that we can really very much enjoy, developing these bridges and doing it, especially with our colleagues, with our students, with our younger fellows. So there are, of course, different perspectives to how this developed. There is, for instance, this interesting article by Professor Fradkov from the Soviet Union about the early history of machine learning. They are basically, he says, well, and he is to some extent right. When you look to the basic concepts that are being employed in modern artificial intelligence, you still see the old names, right? You still see the names of Pontryagin, right? In control theory, you see the name of Kolmogorov. You know, we all know Kolmogorov for his fundamental contributions to probability, to partial differential equations, also for developing modern functional analysis and coining the first ideas and concepts, allowing us to tackle complexity, right? And then he says, well, you know, what we call nowadays machine learning is very often a compendium of all this classical know-how. Also, of course, you know, Kantorovich in optimization, Monge Kantorovich for optimal transport. You see all these old names. So he says, this is a modern compendium of all these ideas, but of course, put in a way that it becomes something of, you know, easy and universal use. And this was probably the great breakthrough of ChatGPT and DeepSeek. It's not that artificial intelligence or machine learning works. It does work. But in fact, you know, the magic is that it can even work on our pockets, and that instantly you can have, you know, the answer to the questions you are, you know, thinking of. But on the other hand, there is a traditional control theory. You are all welcome to have a look to this report that SIAM, the Society for Industrial and Applied Mathematics, published back in 2003 on the state of the art in control theory. I like the image of the front page. I think you can download it from the SIAM webpage for free. The PDF, you can get it for free. And in the front page of the printed version, you see this image, right? And here you see some of the most relevant historical applications of machine learning. So this is, for instance, a thermostat, right? So nowadays, thermostats don't look anymore like this, right? But this is the classical thermostat whose goal is to regulate temperature, right? And the way the thermostat operates is by the classical concept of bang-bang control, right? Right? So typically, we are interested on regulating the temperature on a room. We start maybe from a temperature that is very high. It's like 27 degrees now in summer, and we want to regulate the temperature maybe to 23, right? So what do? Well, we inject, you know, hot and cool air in a Bangman manner, in a piecewise constant manner, so that the temperature is brought down from 27 to 23 and then kept oscillating a little bit around 23. If you will look to how the temperature profile is in the room, you will see that even though, you know, the air conditioning is very efficient, the temperature is not really to be constant 23 exact. It will be slightly oscillating around 23. Why? Because as soon as we turn off the air conditioning, the temperature will go up. And as soon as we turn on the air conditioning, then the temperature will go down. And the role of the thermostat, which is a sensor, is just to measure temperature in the room and to decide whether we should go into on mode, because temperature is too high, so we have to cool, and then we have to turn on the air conditioning, or whether we have to turn off because the temperature is already sufficiently low, right? So the sensor is basically measuring whether we are below or above 23 in order to turn the air conditioning on or off, okay? So this is the classical thermostat. This is the first airplane of the Wright brothers, right? This was the, you know, the pioneering contribution to aeronautics. This is a modern airplane. I think this is a biological cell in order to, refer to the modern applications of control theory and biomedicine. You see here a microchip. You see here a robot. You see a telecommunication network, another telecommunication network in a conflictual scenario. And we see here the first picture. So what is the first picture? The first picture actually refers to the governor, right? The governor was precisely the first control mechanism that was introduced during the Industrial Revolution and that allowed, for instance, to optimize the performance of the steam engine and the trains. Trains were the first contribution to, transportation, communication, and that facilitated the Industrial Revolution. The goal there was to keep the pressure on the steam engine uniform in order to keep the performance of the locomotion engine steady, in a steady configuration. And for this, the governor scheme, the governor mechanism that was analyzed. So this is the name, governor mechanism, whose analysis was developed by Lord Maxwell, the same Maxwell as in electromagnetism. He made the first mathematical analysis of this model, and his pioneering paper is very often considered as the first scientific mathematical article in control sciences, okay? So we see that control theory has been developed since basically the Industrial Revolution for now almost 200 years, right? And this evolution has been very often in parallel to the, say, a slower evolution of applied mathematics that took place mostly during the second half of the 20th century. Very good. Concerning the history of control, I have mentioned to you this paper by Fradkov on the history of machine learning. We wrote a paper, long paper, 60 pages, back in 2003 with my colleague Fernandez Cara in Spain on the history of control theory, and it is also available online freely. So now, going back to the state of the art in applied mathematics, as we said, continuum mechanics, partial differential equations, analysis and numerical analysis, this is more or less the trend, right? The process, how the methodology of applied mathematics is developed. So first, modeling and mechanics, partial differential equation as a prototype of model in order to, mimic the industrial or biological process we are considering, then analysis, and finally numerical analysis, of course, with a lot of pre and post processing like parameter identification and control problem, optimization and control in the end. But basically, the way we work, we all know, right? So to begin with, we need a partial differential equation. We need to know, right, what is the model in analysis, the ODE or the PDE, that better represents the process we are handling. And in partial differential equation, we know, I mean, it's the first chapter in every book. It says, well, you have different partial differential equations, but there are different types like elliptic, parabolic, and hyperbolic. And it's very important to have an idea of how differently each of them behaves in order to develop appropriate methodologies to understand the physical or technological process that you are considering. This is the first point of applied mathematics, right? So you will hardly do anything in applied math if you don't have a minimum understanding of the prototypical models in applied math, which are always written in terms of ordinary or partial differential equations, okay? This is traditional applied math. Now, when you look to how machine learning operates, you realize that they do it totally differently. So in machine learning, there are just data, right? So if the source for applied mathematics traditionally was the PDE, right? So in traditional applied math, of course I am oversimplifying, but I think this simplification allows us to understand the picture, right? So in applied mathematics, we need to begin with a model from mechanics written very often in terms of PDEs or ODEs. In machine learning, you rather start from data. Data is all you have, right? So maybe you are dealing with a very complex problem for which we don't have a good, say, PDE or ordinary differential equations. For instance, I would like to understand, the dynamics of the Mensa on campus. How many people are coming every day to Mensa, at what time, what kind of food they eat, right? So this is probably something that is very hard to model using a partial differential equation. Do you think we can use a heat equation or a wave equation in order to understand and anticipate how many people today there will be at Mensa? At Mensa, say at 12, and at 12:15, or 15 to 12. So that's very hard. So we are rather dealing with data. What we know, what we'll have is plenty of data, right? They will have the records of past days, and they will know how many people were, how many people were eating this dish or that other dish. So machine learning is rather built, on the foundations of a big data set, right? But then the question is, what do you do with these data sets? We were trained to do partial differential equations. Now what we do with data, right? So probably the first question you can ask, and this is what the Lloyd algorithm was developed for. So the first question will be classification. If you give me data, can I classify them? This is probably the first thing to do, right? It's the same as, a professor at university, you have to classify students getting the mark A, B, C, D, E, right? Or, you as a student, you have to, organize your tasks, assigning different segments of your agenda to study this topic, this other topic, this other topic. So classification is probably the first thing you have to do. Every time you have data, you have to organize them into clusters, right? So now I ask you, could we, now we are here, I don't know, 20 people, or 25, I don't know. Can we split this group into two subgroups? So given a set of data, like the audience in this room, can we split it into two parts? Yes, of course we can, right? But the answer is not unique. You see that this problem is not well posed in the sense we are used to. So what does it mean, well posed in the sense of Hadamard in partial differential equations? It means that if you give me data, like initial data, boundary conditions, right-hand side, the partial differential equation has one and only one solution in a given functional space. This solution is continuous in time. You have some stability properties. We expect all these from the concept of well-posedness. When I ask you, can I classify data into two subclusters, subgroups, subclasses? Then the answer is yes, of course. we can, but we can do it in so many different ways that the question doesn't really make much sense, right? I could classify, how could we classify people? We could say we classify right and left. Well, there are two people here, then we can decide whether we put the boundary here and then you are to the right, or we put the boundary here and then you are to the left. But we could also take those that are up front and behind. We could also say, oh, depends on t-shirts, right? Then black t-shirt and white t-shirt. Oh, but there is one with a pink t-shirt. So what we do with pink? Well, pink we put it with, say, white. Or pink we put it with black. So you see, the problem is not really well posed. So thinking on this topic, Lloyd, so he was an electrical engineer, and I think an engineer, I think in the 50s, right? I think he was working in Bell Laboratories, right? This text is taken from the Wikipedia, where you can find more information about him and his work. He had the following idea, right? And this idea actually he said, let me try to develop an algorithm that will classify a data set systematically. So he took a data set, assuming the data set covers, for instance, this rectangle, okay? So assume my data set covers this rectangle in a very dense manner. So classifying data is like splitting this domain into different subparts, right? And then in this particular example, he said, let me try to split the set into 1, 2, 3, 4, 5, 6, 7, 8, I think, 8 subsets, okay? I tell you, divide this rectangle into 8 subsets. Well, you will tell me this is very easy to do. But again, there are many ways I can do. I can just do vertical strips. I can do horizontal bands. I can divide in 8 small rectangles. I can do some diagonal cuts. I maybe can do some random cuts. There are many ways of doing this, right? But the interesting observation of Voronoi is that you can relate these different splitting strategies to the dynamics of a dynamical system. And this is the dynamical system he generated, right? Let me see if the video works. This is the dynamical system he generated. You see, we start from some configuration, initial configuration, which is more or less disordered. And after a number of iterations, it has the tendency to converge into some more homogeneous distribution of a space into 8 different subsets. Of course, these subsets, this constitutes a Voronoi decomposition. Each of the subsets is a polygon, right? They are not, of course, all equal. The sizes are more or less uniform, but they are not identical. And of course, the shapes are not all identical, right? So how does Lloyd algorithm work? So the idea of Lloyd was the following. So you want to split this into 8 subsets, right? So then what Lloyd proposed, Lloyd Algo, he said, take 8 initial points at random. You choose 8 points at random. For instance, this one, this one, this one, this one, this one, this one. How many have 4 and 8? Okay, you take any 8 points at random. So in principle, each person could choose 8 different points, and therefore applying Lloyd algorithm, you will get to 8 different decompositions, 8 different splittings of the same domain, but with different subsets. He said, start from this configuration. Now, this is the initialization. Second step, allocate to each point the polygon made of points which are closest to that point. So these 8 points are like the capitals of 8 different provinces. And now you have to allocate the piece of land that each capital will govern, right? Then, for instance, this point here has to belong to this region, because clearly this point here is the closest to that one. This point here has to belong to this region. This point here has to belong to this region. Maybe when you are here, well, you hesitate whether it should be here, there, or there, but this is something you can carefully do, and in this way you will determine some kind of initial splitting, right? It's certainly not correct what I'm doing, but I mean, you get an idea. So you do these regions allocated to each capital. But once you have done this, you realize, well, but you see, the capital, this one, for instance, is not really at the center of the region. And it will be better to have the capital of the center. Why? Because in this way, you are minimizing the maximal distance to the points within the region, right? This is a geometric optimization problem. If you give me this region, this, for instance, Voronoi, pavé, this rectangle, and you ask me what is the best location for the capital, I will tell you it should be the center. Right? Why? Because whenever I am at the center, I know that I am minimizing the function maximum of distances from the capital to all points on the domain. So this is a min-max. Okay? So now I take each capital and I move it to the center. Sometimes very little, sometimes maybe a bit more. So in this way, I have completed one iteration. You see, I started from 8 random points, the crosses. I allocated the corresponding Voronoi pavé polygon, and then I recollocated the capital from the initial position to the center of this pavé. So I have defined one iteration. And once you have seen how the first iteration has been done, then you can repeat. And you repeat, and then you generate this kind of random dynamical system whose, by the way, I think dynamical system properties are still, not very well understood from an analysis perspective, right? So this is a way of implementing Lloyd algorithm. Of course, you understood that I can initialize Lloyd algorithm in the opposite manner by saying, well, instead of choosing points, let me take a partition, right? So 1, 2, 3, 4. So is now okay? 1, 2, 3, 4, 5, 6, 7. You can take an initial partition, and then you can do it. How? Well, out of the initial partition, I take the centers, right? And once I have chosen the centers, I reallocate the boundaries, right? And in this way, you build an iteration from initial boundaries to future boundaries. And again, if you iterate, you will get the same kind of stochastic dynamical system. Very good. This is what is called in practical applications in machine learning, this is called unsupervised learning. So what does it mean, unsupervised learning? Learning is, of course, the objective of machine learning. What does machine learning mean? Actually, maybe we should have discussed this from the very beginning. What does machine learning means? Well, we expect machines to learn and in this way do our own work. And this has been done very successfully. For instance, you can take your, any document in Chinese and you try to translate it into English or reverse. Of course, this is something that we humans can do, but it takes a lot of time. Now you can do that automatically using DeepSeek. You just put the text in Chinese or in English in DeepSeek, and you get it automatically translated. So machines have learned. But how do you learn? Normally, to learn, you need information. You need a book. You need a book to read, to understand, to memorize this basic information, based on which you will be able to develop later your skills, right? But to learn, you need supervision. So here, in Yoid algorithm, unsupervised learning refers to the fact that we are given data without any extra information. So then it will be very, very hard to get a very convincing answer. The question was, split people into groups. Well, we could do it by glasses, no glasses, ages. So it's very hard to do. So this is unsupervised learning. Unsupervised learning, therefore, is a very important concept, but you have to keep in mind that unsupervised learning will never be something extremely sharp and very adapted to the application you have in mind. You can use unsupervised learning maybe as an initialization of the process, a way of, splitting information into different subclusters, and maybe thinking on a, parallel computer, kind of exercise. This will allow you to break down a very big data set into smaller pieces in order to allocate one of these subsets of data to each of the computers. But there is not really information adapted to the application you have in mind that is built in this process. This is why we say it's unsupervised. It's not informed, right? It's just a brute data set that you split as when you cut paper with scissors. Okay? So in most practical applications, we are not interested on unsupervised learning, but we are interested on supervised learning. And this is, one of the topics we are going to discuss here. How do you tackle supervised learning from the perspective of applied mathematics? And this is what, how supervised learning is tackled. So this time, the data set is more informative, is more elaborated, right? And the data set, maybe you have n data, right? You have n data, and the data, so this is the input, and this is the output, the label, right? So this time, not only you have endpoints, xi here, but you also have labels, right? Don't we have color check here? No color check, right? No color, only white, no color. Okay. So we also have the labels. So then we know this is red, and this is red. We know this is blue, and this is blue, and this is white, and this is white, and this is, for instance, green, right? So now we have more information. And of course, this more information allows us to, it's already telling us the nature of this information we are given in the label. Is also telling us what is our criterion of interest, right? Because when I observe people and I watch the t-shirt, either black or white, then, and I note black or white, I know I am interested on the color of the t-shirt. If I note, by the contrary, no glasses or glasses, then I am, rather interested on whether people are using glasses, right? If I look, lady or gentleman, then I am, rather interested on gender issues. When I note a student or professor, I know I am interested more on seniority, issues and the splitting of the community at the university on campus onto basically, professors and students. So the labels already indicate what is, the question you are interested on, right? Or when you take the blood test of an individual going to the hospital, you already see a few indicators, right? For instance, cholesterol. Oh, this means that someone in the hospital has already chosen a priori cholesterol level as being one of the main criteria in order to measure the, individual health. Okay? So the label already tells us, orients, is focusing our attention on pointing our attention into some directions. But not only is giving us, an orientation of what is the main goal, the main purpose of the machine learning exercise, but it contains also a lot of information because it says, right, that, black has to be with black or blue with blue, right? That green is isolated, right? But that there are, whites here and there are reds here that maybe should go into the same group. So these give us clear ideas of how the, splitting of a space into different groups has to be realized. And the way this is typically done in machine learning is quite elementary, apparently, but extremely successful, as you see. The way this is done is rather simple. So it basically consists on the following ingredients, right? So now the goal is what? The goal So maybe these data are maybe in the Euclidean space Rd. This is the dimension of a space. And the dimension of this Euclidean space can be arbitrary. Imagine I'm just, we are taking photos of each of us. We have photos. So what is a photo? A photo is the union of a number of pixels. But the number of pixels depends what? Depends on the resolution of the photo. If I take a very coarse resolution, maybe it's 28 times 28, this is 700 something. So maybe this photo will belong to an Euclidean space of dimension 700. But if I take a very high resolution photo, there will be millions of pixels. So then this photo will belong to the Euclidean space of a very high dimension. This is why one of the issues that is always relevant in machine learning is that we are often dealing with problems in very high dimension. Contrarily to the context of partial differential equations, where we are basically dealing with what? 1, 2, 3 space dimensions plus time. Right? So partial differential equations typically, not necessarily, but typically, in most of the applications we think of, there are essentially 4 dimensions, 3 for space and 1 for time. But here the dimension really depends on the number of parameters. I mean, if you take the academic records of a student, then, maybe 4 years of bachelor, in every year the students have taken 8 courses, you have 32 different, say, grades. So each student will be represented by a vector of dimension 32. Depends on the application you have in mind. Okay? So, but now we have input, and we have the labels. The label can be one scalar, like color, but it can be also a vector, right? It can be which color, which kind of, I don't know, telephone you use, you know, whether you bike or you don't bike. I mean, it can be also a vector, okay? But let's think on the simplest case where, right, the map goes from the input space RD into the space of labels R. What is the goal? Well, the goal is very simple. The goal is more or less to find a function, right, so that the function f maps inputs into outputs, right? But is it true that this is the goal? If this is the goal, well, the task seems very simple, right? Also very many, you know, a lot, very boring, right? Because you see, here I gave like 8 data. It was very easy to allocate the different clusters, right? Red with red, then blue with blue, white with white, green. Then I could build a function that is piecewise constant, like a simple function in the Euclidean space that takes different constant values on each of these subsets. It will be very easy to do. But of course, if you give me a very big data set, so what is the population of humans on Earth? It's 8 billion, right? Right? It's 8 times 10 to the power 9. It's almost 10 to the power 10. So if I take all the individuals on Earth and I allocate a different label for each person according to, you know, its own, say, characteristics, then I will have to build a function that is passing through, you know, 10 billion points. This will be extremely, you know, painful to do. So this is not really the goal. If this were the goal, it will be very tedious, but very simple to do. The goal is much more ambitious. The goal is not really to make it equal. The goal is not really to make it equal. This is not the goal. The goal is to just make it reasonably close, but under a very important condition, is that it generalizes well. What does it mean it generalizes well? It means that this function f has learned from the data set. And this is why we say this is a supervised learning exercise. We expect the function learns. Learns means by trying to understand how the label is allocated to each input, now whenever there is a next person coming into the room, we can really rapidly say, oh, this is a student or this is a professor. This is a master student, is a postdoc, or is a PhD student. Or this one is coming from the Faculty of Mathematics, or rather from the Faculty of Physics. This is what we want. And this is the aim, right? The aim is not only to be able to, and this is what ChatGPT or DeepSeek do. I mean, DeepSeek or ChatGPT are not just a very big reservoir of answers and questions and answers. No. So the beauty of DeepSeek is that you can ask the question you like, which is totally new. Maybe it's related to other questions that DeepSeek has already seen. Because if you ask to DeepSeek, what is machine learning? Certainly other people have asked a similar question, but maybe not in your language, maybe not exactly with the same words. Despite of this, you know, to be able to give you an answer. And if the answer is too long, then you say to DeepSeek, can you please give me a summary of this? And then it says, yes, of course. And then I give you, instead of one page, I just give you one line or one paragraph. So this is the goal. The goal is not to interpolate. Interpolation we knew. You know, you can go to the classicals and you see that mathematicians historically, they have been interested on interpolation. Interpolation you can do. But it will be very, very, painful to build a polynomial, right, that is able to interpolate all the population on Earth. It will be a polynomial, a monster of degree, 10 billion, right, oscillating very, very much. We can do that, but this is not what we want. We want something of a much lower complexity. We want to reduce the complexity. And for this, we have to give up on being exact, but just approximate, but approximate in a way that we learn the essence of the hidden process. The idea being that in this data set, there is relevant information that we can learn from. Right? This is, for instance, what universities will try to do, right? When designing the new master programs, right? I mean, we have a guess. We know nowadays students are interested in applied math, but they are also interested in machine learning, right? And then we cook a new master program combining mathematics, data science, computer science, and then we wrap up this program within a given name, and we advertise it, and then we see whether the students come or not, right? So there is already some information built in the system, but it's not written anywhere. So the goal of machine learning is to realize this implicit information into a function that we can employ systematically, and in a way, at least to some extent, than previous large language models like ChatGPT. But certainly one of the reasons for the success of the next generation of the large language models is that they are using all the know-how of previous large language models. Right? In particular, right, you can use previous large language models in order to generate many new synthetic data. What does it mean, synthetic data? Is that once you have a tool like ChatGPT, you can build new data because whenever you ask a question, input, you will get an answer, output. And you say, to begin with, I have just 8 data, but now because I have the toy model, with the toy model, I can generate many more data. And when I generate many more data, probably, the function f will adapt, and this will lead to a process of self-adaptivity, which is precisely what we are observing in each generation of large language models that we are offered. And now there is not only ChatGPT and DeepSeek, there are many, many others, right? But this is the goal. The goal is not to be exact. It's not interpolation. It's not interpolation. It's not exactness or precision. Is rather generalization. And generalization is much more about, finding a low level of approximation of a given data set. Now, as I said, we do this, I will explain this later in much more detail, but basically we do this, we have to choose a class of functions, right, to do it. So how do we choose in which functions f we can think of? We could think on polynomials, we could think on trigonometric functions, on finite elements. In machine learning, we rather choose neural networks, right? So neural networks is just a function that is defined in a discrete manner. So we will put here the input, the x, and we will hit here, get here the output, the L. And then this function is defined just through a network. A network is just a graph. If I draw the network that way, it looks like a linear graph that is described just by the connectivity of matrix, that is just telling me what is the intensity of the communication in between two nodes, each of the nodes. And the coefficients of this matrix will tell me how this network is configured. We could build the network, for instance, of WeChat of these team members. I don't have the WeChat of all of you, but I have the WeChat of Sikian and Senan, for instance. So I will have a 1, right? In between these two nodes, there is a connection. In between these two nodes, there is a connection. This is certainly not sufficient. But probably Sikian has the WeChat of some of you, and then some have the WeChat of others. Maybe we are all connected. Who knows? Right? So it's just a linear graph, but in a deep neural network, we are not just using a linear graph. We are mimicking the behavior of human brain. And to do this, what we do is we say, well, each of these nodes will not just be a node of the graph, will be actually a neuron. And you know what you have to do to make it a neuron? You have to endow this node with the possibility of being either on or off. So a neural network is just a linear graph in which each node, as in classical control theory, it has a thermostat built in so that the neuron can be on or off. So you don't necessarily use all neurons. You just use those you need. And if you don't need them, you just turn them off and keep, them for later. Okay, so then I have to determine a number of coefficients. So the connections between all these neurons, whether each of them is on and off, this leads to a number of parameters, and the function has to be built by just optimizing these parameters in order to minimize the empirical risk. What is the empirical risk? It's just the gap between, the input and the output through the function f defined by this neural network. As I said, I don't try to fit exactly. It's not interpolation. I just try to minimize the global error. And this global error can be just built by averaging the errors in each of, the data of my data set. For doing this, I have to choose a loss function, a norm, a distance. I could take the L2 distance. I could take some L1, some LP, some L infinity distance. There are many distances you can use, right? But this is the idea. And of course, as classical in optimization and control problems, and also in inverse problems, in order to guarantee that the minimizer exists, you need to guarantee to assure that the functional is coercive. And for this, what you do is you add some regularization term employing some alpha parameter. And then, when you look to the problem, you say, well, but then the problem is trivial, because whatever is the architecture, there are a finite number of parameters. This functional is continuous. You give me the data set, I build this functional is continuous, is coercive. A continuous and coercive functional in a Euclidean space has a global minimizer. And these are the best possible parameters of the neural network I can choose. So that's basically the summary of supervised learning. Okay? Tackle supervised learning problems, then you will immediately realize and say, well, but this is not new. This is what Legendre and Gauss did 220 years ago when they formulated the classical paradigm of least squares. Already at that time, and it's not because they were weak mathematicians, they were extremely strong. They knew interpolation theory, but they also realized that interpolation theory had a limited scope. It's very important, of course, and we use it a lot, but not always. Because if your data set is very, very large, interpolation methods will lead to such an oscillatory function that it will be first very hard to build, and then so oscillatory that it will have kind of a fractal structure. It will be very hard to use. So they said, maybe we should change the perspective. And this is how they introduced the methodologies related to least squares. So in least squares, given a data set, like the red dots there in the different images, right? So this cloud of points on this cloud of red points or this cloud of red points here, the idea is not to build a polynomial that passes through all of them. This is something we can do, right? You take your iPad, your tablet, and you can, with your pencil, you can certainly solve the interpolation problem. Excuse me. What they said was, listen, let's do it differently. Let us adopt a very simple model like this blue parabola, and try to find the blue parabola that better approximates this cloud of points. Is this parabola interpolating the points? Of course not. So in a parabola, how many degrees of freedom you have? You have 3 degrees of freedom in a parabola. ax squared plus bx plus c, a, b, c, just 3 degrees of freedom. And here there are many points. So you don't expect the parabola to pass by all these points. But you see in this picture, you clearly see that the parabola somehow is extracting the essential trend of this data set. Okay, so, and then how does least square works? Well, you could say that least squares is really exactly the same we do in supervised learning, right? So somehow least square is the ancestor of supervised learning. Of course, the difference is that, least square was built in 1805, 220 years ago. 200 years ago, not ChatGPT, no DeepSeek, not iPhones, no Huawei, no computers, no internet, right? So everything had to be solved analytically. This is why at that time, they were thinking on very elementary models like linear functions, right? Parabolas, ellipses, right? Simple objects you could, more or less try to compute the values of, right? For instance, when the model is linear, we say this is linear regression. Well, it's just about optimizing the coefficients A and B. If the model is linear, the function is going to be y equal to ax plus b, right? Well, if x is in Rd, right? If we are dealing with linear regression and we are dealing with functions from Rd to R, how many free parameters you have? Right, so in this case we have d plus 1 parameters, right? Because a dot x is a scalar product, a is a vector, a1, ad, so you have d parameters on a, and then b, the shift. So it's these plus 1 parameters, but that's all. This is the complexity you can allow. So this was the original idea of least squares, but they were doing exactly the same. They were simply minimizing, right? The total, the empirical risk, where I define the empirical risk, is nothing but the Euclidean norm of all these errors or residuals. This is why it's called R, right? R is the residual. Is the gap between the label, which is called here y, yi, minus the predicted value of the function you are considering on the data set xi, on the inputs, depending on the parameters beta chosen, that there will be the a, b, d plus 1 parameters. You just minimize this. That was least squares, and this is what we do. So essentially, we could say that, supervised learning is very much like least squares, except that now, what are the different features that we experience when we are dealing with, supervised learning, model supervised learning problems? First, as I said, the dimension the dimension D can be huge, because maybe we are dealing with very sophisticated data, like very high resolution images or a video. It's in a huge dimension. The dimension D will be huge. Typically, we are also dealing with giant data sets. You know, we are dealing with the population of a country, so millions of data, right? Or billions of data. So the scale of the problems is huge. And because the scale of the problem is huge, we also need to increase the complexity of the function, right? We don't expect just to be able to do it with, you know, just a few parameters. So we need to increase the dimension of the model. And this is why we adopt a neural network, where there are plenty of free parameters. But we don't adopt only the neural network simply because of a matter of size. So we don't adopt this point of view of neural network simply because here, by increasing the number of neurons, there are more coefficients, and therefore the complexity of the model increases. I could have done that also by using polynomials, right? I can increase as much as I wish, you know, the number of parameters by choosing polynomials of higher degree. We adopt this perspective for a good reason. And the good reason is this idea of neuron or bang bang. Because somehow, bang bang is what you need to classify. Very much like in the initial algorithm of Joy. The idea is already in the initial algorithm of Joy. Well, Joy, we don't use it too much. It's heuristic, it's very random. We know that Joy can lead to many different outputs depending on how you initialize the process. It's not a dynamical system like a heat-like equation in which there is an asymptotic attractor that is determined a priori. Depending on where you start, this already determines very much, more or less, the end of the process. It's very, very sensible to the initialization. But the idea of interfaces splitting, the composition is already built in. And this is precisely something you can achieve by the fact that each neuron is allowed to switch from on to off. Basically, whenever you say on and off, you are splitting. This is like traffic management, right? So traffic management in a city is extremely complex, but there is something we all understand. Every light does, you know, a very significant, has a very significant impact, because just by switching from green to red locally, you transform radically the flow of traffic. Either cars have to stop or they are just, you know, invited to go. It's just this switching from on and off. So this very idea of on and off, bang bang control that each neuron is realizing is fundamental in the model of adopted through neural networks. It's not just a matter of size, it's a matter of nonlinearity, right? Because you see, and this is very important, and I will discuss this in detail in this lecture. So it's linear versus nonlinear approximation. So you see, when I formulate the problem of least squares, right? In the same way that Legendre and Gauss did. So this is linear regression, right? So this is linear regression. This was done by Legendre and Gauss back in 1805. And then the goal here is to minimize with respect to A in RD and B in R, the average residual, the average Euclidean norm of the residual. That's all. So this is a linear approximation process. Why do I say that it's linear? Well, you will say it's not linear. I mean, this is quadratic. Yeah, the function to minimize is quadratic. But the model is linear. It's not linear because it depends linearly on x. When I say that this is a linear approximation process, it's because f depends linearly on a and b, right? So the dependency from a, b, the three parameters into f, this is a linear function, right? So the map from parameters to function f, right, is linear. If you just multiply a by lambda, ab by lambda, or you add a1, b1 plus a2, b2, the output model f depends linearly on these parameters. So this, right, this function from the space of parameters AB in Rd plus 1 into F, which is in the space of models under consideration, this function is linear. As soon as we say that each neuron can be either on and off, on or off, this becomes a nonlinear process. And therefore, we are within the class of nonlinear approximation theory. Right? So this is a very important step. Whenever we go from linear regression, classical least squares to neural networks in supervised learning, we are moving from linear models into nonlinear models. And this, as we will see now, introduces a lot of opportunities, but also added difficulties. This is very well explained in this series of videos that I invite you to have a look. Maybe if we have time, we can watch part of one of them in this channel 3 Blue 1 Brown, where they explain, the basic mathematical ideas of how neural networks work, how machine learning is built, large language models, and so on. So there they explain, this is for ChatGPT 3, right? ChatGPT 3, which is the free version, is not ChatGPT 4, uses 175 billion parameters. So 20 more times the humans on Earth. So it's true, you have finitely many parameters to be optimized. Yes, there are finite, but there are too many, right? I mean, this is not something you will do by hand. The biggest supercomputers in order to be able to train. This is why, these large language models, not everyone can develop a large language model. You can use it, but I mean, to develop it, you need to train such a monster with so many parameters. This requires a lot of energy and the biggest supercomputers. So this is ChatGPT 3, the free version. ChatGPT 4, the commercial one, that has to pay like $20 per month or so. I think it uses like 1 trillion parameters. So you see that in this setting, we are very much on the context of the course of dimensionality. So the course of dimensionality was introduced by Bellman, right? It was in the context of control, right? It was in the 60s. It was in the 60s in the context of control, right? Where he said, well, you see, in control theory, after all, it shouldn't be that difficult. Because after all, what is control theory? Send a rocket from, say, the Earth to the moon, right? Or design, the optimal trajectory to go from, the lecture room to Mensa. Well, we should be able to do this, right? To just find the geodesic. After all, it should be just a matter of think, for instance, on broken lines, right? Right? Like in Brownian motion, at every point, you have just to decide whether you move forward, backward, left, or right. It shouldn't be that difficult to do. Well, what happens? It happens that when you are in very high dimensions, so we were in 2D, there are only, forward, backward, left, and right. If we are in 3D, the number of options increases, right? And when you are in dimension D, every single step belongs to a class in which you have 2 to the power D possibilities, right? So in 1D, it's just left or right. In 2D, is forward, backward, left, and right. It's okay, 2, 4. If we are in 8D, well, it's more complicated, but there are only 8 possibilities. Fine, we still understand. Yes, but when you are in D dimensions, right, the number of possibilities in each step is 2 to the power D. And you have to do many steps to move from the origin to destination. So the number of possibilities for the possible paths you can think of, you can consider, is so huge that nobody will be able to figure out what the best one is. Because you want not only to find one, but you want to find a path that is nearly optimal, right? You want to go in minimal time to Mensa or close to minimal time. You don't want to get lost within campus to spend 1 hour to go from here to Mensa. Because we have to go back for, Professor Sao's lecture. So it's very simple, apparently, but the course of dimensionality means, even if it is very simple, you will never be able to do it because the number of possibilities is simply too huge. So here we are very much in this context, but also facing the devil of non-convexity. And I think this is also one of the topics that Professor Sao will lecture on. Because you see, the idea of Legendre and Gauss was, if you take this linear model before and you do least squares, well, you are in dimension D, but we are minimizing a paraboloid. The function I wrote before with respect to A and B in this linear model of linear regression and least square is a paraboloid with respect to A and B. Therefore, there is a unique global minimizer. It's very easy to compute. And it shouldn't be that difficult to develop a, descent algorithm very much based on gradients, right? Which leads to the minimizer. This is gradient descent, and there are many versions, right? In optimization theory, there are many versions to minimize successfully convex functions. Gradient descent is maybe the starting point of gradient, conjugate gradients, and so on. Okay, very good. But now, as we said, we have modified our model to make it nonlinear. And what happens with nonlinear functions? As soon as you embed a nonlinear function within the square, right? The question becomes, do you think a function like this will be convex when sigma is something like a bang-bang function? Because in our model, yes, there is a square, right? In supervised learning, the idea was the same as in least squares. We minimize some loss function. Yes, but within the function, I have embedded on every neuron this possibility of switching from 0 to 1, or from 1 to 0. So is this function going to be convex? So what do you need for the square of a function to be convex? Or maybe more generally. So I give you two convex functions, and I do the composition. Is the composition of two convex functions convex? What do you think? You take one convex function, another convex function, you do the composition, is the output convex? No? Why not?
Maybe there is a theorem I know before. The F may convex, but he needs to be
increasing, right? Yeah, there is something about this, right? Yeah, we all recall something about this. One has to be careful, right? As soon as there is some composition and we are dealing with convexity, it's very easy to lose track and our intuition can easily fade. Let's look to the convexity of the composition. What is the first derivative of F composition G is F prime at G times G prime. And what is the second derivative? The second derivative is I do the first derivative of this, then I get F second prime, then G prime square. And then there is the second derivative is F prime of G times G second derivative. So if F and G are convex, the convexity is not guaranteed. This is positive, of course, because F is convex, second derivative non-negative, square non-negative. This is non-negative, but this here, this one is non-negative, very much depends on the increasing character of F. So you can imagine that you say, oh, but you know, when I go in band control, when I go from 0 to 1, I am increasing. Yes, but when you go from 1 to 0, you are not increasing anymore. So convexity will always fail. And therefore, we will be in a situation that like this, except that this function, right, will be defined in a Euclidean space where the dimension is maybe 175 billion parameters. So can you imagine looking for the global minimizer of a function defined in a Euclidean space of such a big dimension? Well, it's very hard to figure out, right? What we know is that even in 1D, finding this global minimizer will not be an easy task. So what is the state of the art on this, Professor Zhao? So what can we do there? Maybe some random, deterministic will not work, right? Because if I say, okay, I initialize the process here, so I'm here and I apply a steepest descent, I will get here. So finding a local minimizer looks simple. I just need to start from wherever on the landscape of the functional I am, and then decay according to the gradient. This will lead me to a local minimum. But who guarantees this is the global minimum? There is no way. So, and if I don't have a priori knowledge of the landscape of the functional, and this is what happens because you have this monster network and this monster data set and this huge amount of parameters to be tuned, and you have to find the global minimizer, you don't have any clue or where this global minimizer is. Then you don't know this. You don't have access to this plot. So you don't know that you have to look in this valley. And therefore, the likeliness that you get into this valley is very low. Basically, the only thing you can do is randomize your process and from time to time start again, right? So I start from here, I get there, and it's a nice local minimizer, but maybe it doesn't generalize as well as I was expecting. I have to do something better. What do? I start from another configuration, hoping that maybe this time I get into this well, and therefore by minimization, I do better. And whenever I am deeper and deeper and deeper, then what I expect is that my functional will generalize better and better and better. So this will, be a better tool in order to, generalize, to predict, because this is the goal, right? So this is, for instance, what the hospitals want, right? The hospitals want to learn from previous experiences so that whenever a new patient comes and they do a blood test and they see these parameters, they say, oh, maybe hepatitis, or maybe some cardiovascular disease, or high blood pressure. I mean, they immediately want to, and we want these functions to generalize better and better and better. This is very much related to how deep we are on these wells. But I insist, non-convexity and very high dimension. The two together make it impossible to humans. This is why large language models could only be developed once computer science, scientific computing, and computers develop very, very successfully. Of course, what I said that, supervised learning is just taking a neural network and then minimizing a loss functional is only part of the truth. There is a lot of engineering and science and smart people involved on this, right? So when you look to comments on for instance, how, WeChat is working, they talk, for instance, about the mixture of expert models. So there is not only one model, there are several models, several neural networks, several architectures, and then the combination of the different architectures is what is employed in order to better learn, right? And then the switching between the different architectures is also something that plays a critical role. There is also a lot of, other than supervised fine-tuning, fine-tuning will be, fine-tuning means try to get deeper and deeper and deeper, right? So refine is like multi-scale numerical analysis. You start solving a PDE maybe on a coarse grid, but then you make the grid finer and finer and finer, right, in a post-process, so to get better and better and better resolutions of the solution. So fine-tuning is a very important idea. And then reinforcement learning from human feedback. Also, post-process by, individuals employing, the large language model to say, well, the large language model seems not to be able to say, to add well numbers. Oh, we'll have to work this out, right? Or maybe, it does, addition is okay, but multiplication is not good, right? Or, oh, it does very well this type of exercises in mathematics, but it seems that it didn't learn enough about physics. So then you have to keep, fine tuning. This is reinforcement learning by human interaction, right? So you just, have a colleague to whom you ask to learn better about the specific topic. So this is a very complex process, and this is what has led to, the huge success. And now we are on a race led basically, I think, by US and China, I will say, right, about, to develop more and more and more advanced tools in artificial intelligence. Now, what is the role of humans on all this, right? So what we as humans do, and this is important to know, right? Because, we are here discussing in these lectures, we are trying to learn, we are all interested on doing something on this area. Yes, but as humans, what can we expect to do? The problem is so complex, it's so high dimensional, what can we do? What are the limitations for human? And there are here two comments that were done. The first one is this Moravec's paradox, right? It says, what is easy for humans is hard for machines. And what is hard for humans is easy for machines. This is what it says, right? So machines and humans, we operate differently, right? So adding is easy for machines. This is why we have to add a lot of numbers, let the machine do it, it will do it faster. This is the role of classical computers. But thinking is much easier for humans than for machines. So we have to complement each other. This is the first comment. And the second one, the bitter lesson from Rich Shatton, it says, the biggest progress in AI has come from general methods that leverage computation rather than methods that try to incorporate human knowledge. So what does it mean? It means that if you try to figure out, for instance, how many neurons should I put into the neural network to solve the problem? Or if I have to build some kind of activation function to switch from 0 to 1 or from 1 to 0, what is the best function that will do this switching? I mean, these kind of problems, analytical problems, are very hard to anticipate by humans. So it's better, right, to let the machine do it. So what humans have done has been to build sufficiently large neural networks on which there was sufficient room for the problem to be satisfactorily solved. And then let the machine find the solution. So you can think on these machine learning models as being like, we all know the Rubik Cube, right? We know the Rubik Cube. Anyone here has ever solved the Rubik Cube? I'm sure you do, right? No? Who solved the Rubik Cube? No one has ever solved a Rubik Cube? You know what it is, the Rubik Cube, no? How do you say Rubik Cube in Chinese? Huh? You did it? You did it? Yeah. How long time did you need it to do? 7 minutes or 7 seconds? 7 minutes, okay. 7 seconds will be, you know, maybe the Chinese champion, no? Right? Very close to, you know, or maybe the Jilin champion, right? So can you check how much time does the Jilin champion needs to solve the Rubik Cube, please? Yeah. Okay, so you see, now think on a Rubik Cube. The Rubik Cube is in dimension 3, right? It's a three-dimensional object, three-dimensional cube. Now think on a Rubik Cube in dimension 175 million or billion. And for humans, this will be impossible to solve. This is what machine learning is. So we have built a Rubik Cube in very high dimension in which the number of possibilities is extraordinary. So there are so many possibilities that certainly, the function we are looking for that is able to interpolate or nearly interpolate all this data, learn from all this data to perform well, is in there. But please don't ask humans to find it. To find it, you need a machine, because you are facing, again, the course of dimensionality. This is what Shatton says. So you see, the role of humans is not to, you know, fine-tune, try to define in a very deterministic manner what is going to be the best model, the best parameters to realize the supervised learning exercise. The role of humans is to simply figure out in an abstract manner how the monster has to be built, and then let the computer deal with it, because it's going to be anyhow too complex. We will never, you know, be able to tackle as humans this course of dimensionality that is intrinsic embedded to the problem. So what is the Jilin world champ? 20 seconds, okay. Very good. Okay, so now as applied mathematicians, what can we do? As I said, now, given that Moravec and Shatton already said, be careful, right? The role of mathematicians is not to do by hand all these parameter computations that has been already built by the supercomputers to get here. So maybe what we can try to do, and this was the effort of this first lecture, was, you know, can we understand better? Can we explain analytically why all this all works? And the second question, we have been always working with partial differential equations. Analysis and numerical analysis of partial differential equations. Can we use these tools, machine learning, for solving partial differential equations? Or maybe we have to move further and try to think how to integrate the classical know-how of machine learning, of applied mathematics with these new tools of machine learning to tackle, to develop the new era of applied mathematical methodologies that certainly have to preserve all the know-how we have from analysis and numerical analysis, but also integrate all this know-how coming from data science and machine learning. And this is what is about, for instance, the methodologies of digital twins. I mean, in the last SciAm News newspaper, there is an article about digital twins for geosciences, for natural resources, digital twins for biomedicine. So digital twins is this area in which data, math, modeling, and decisions merge, right? It's about, in real time, right, try to merge data with the tradition of applied mathematics so that in real time, be able to determine, right, for instance, whether, a patient suffering of diabetes needs, of a shot of insulin or not, right? So this is the goal, right? Eventually help humans to have a better quality of life, right? By helping them on making these decisions on real time, okay? Now, as mathematicians, we can aim to contribute maybe by understanding better, and maybe, who knows, if we understand better, maybe we can try to explain, and this is a very important requirement, right? In the future, artificial intelligence will be required not only to give the good answers, but also to explain how this answer was achieved, right? So you can think, for instance, on a trial, right? The opinions need to be based on clear arguments, proofs, right? Methodologies in order to be taken into consideration. In that sense, explainability is very important. The robustness of the methodologies, the computational cost, the generalization, the complexity, all these are very important topics that, deserve some mathematical attention, and that might probably contribute to the development of more advanced methodologies. Okay, so let me just conclude with this section, with this slide. Why all this works? Why all this works? Well, the reason for this to work is what is called the theorem of universal approximation. I mean, the first theorem of universal approximation is due to Norbert Wiener in this celebrated paper in Tauberian theorems. Norbert Wiener said the following. He said, give me a Gaussian function, G. So like this function, G. This is the Gaussian G. Then, if you let me translate the center of gravity of the G, right, to different locations, and then you let me choose the amplitude of each of these Gaussian contributions, this linear combination constitutes a dense set of functions. So in particular, right, you take what Gauss said, give me a general function f of x, you can approximate it by a function like this. Of course, you will need to, increase the number of k, but this is typical, the same in polynomials. I mean, every analytic function can be expanded in power series, meaning that polynomial approximations represent the function better and better and better, but the less the error is, of course, the more terms you need in the power series, the higher the degree of the polynomial has to be. That's for sure. So you will need maybe, plenty of k's in order to, approximate your function. But the idea is very simple. You have a Gaussian here, maybe very little, because I have an amplitude W which is small, and this is the center Vj here, and this is the amplitude Wj. Maybe I have a bigger Gaussian here, maybe I have other Gaussians. So if I am smart, on collocating all these Gaussians in their strategic centers, and I combine the widths, the heights properly, this will guarantee the needed density property. Okay, so this was a theorem in harmonic analysis. Actually, the proof of Wiener was thinking on the Gaussian. Why? Wiener said, because the Gaussian has the property that the Fourier transform of the Gaussian doesn't vanish anywhere. Actually, proving this theorem will be a good exercise. Try to do it yourself. You just use the Fourier transform, but you need to use in a critical manner that, the key in the argument of Wiener is that the Fourier transform of the Gaussian never vanishes. And why the Fourier transform of the Gaussian never vanishes? Well, because the Fourier transform of the Gaussian is a Gaussian. So it never vanishes. Now, when Wiener did this, probably he was not thinking on this, but with this, we inaugurated the area of nonlinear approximation models. Why do I say that this is a nonlinear approximation model or process? Why do I say it's nonlinear? So now look. So what are the parameters now? The parameters are the WJs and the BJs from 1 to K. And the output is the sum from 1 to K of WJ, GX plus BJ, right? And this is our model, which is, say, a function in L2 of RD, right? So is this map here linear? So this is chaos, huh? This is Lorentz attractor, right? Okay. So is this model linear or not? So let's see, this is clearly linear in W, right? If I multiply, right, add W, okay, it's linear on W, but is it linear on G, on B? So is this map linear? Right? Is this map from B in RD into the function Gx plus B, which is a function in, say, L2? Is this a linear map? This is a very, just translation. This is the translation map. It cannot be easier, right? We all understand the translation map. It's just like in transport equation. You give me a function f of x, and I define fx plus b. Cannot be easier. This translation is a linear operation on functions. Let's see. What is gx plus b? Right? As Gaussian, I could take, for instance, let's take just for reference the Gaussian exponential minus x squared over 4. Of course, the theorem by Wiener doesn't depend on the variance because it only requires G to have a non-null Fourier transform. I could choose it more compressed or more spread. This is not so relevant. And now let me see, what is Gx plus b? Gx plus b is the exponential of x plus b squared divided by 4. And this is what? This is the exponential of x squared plus b squared plus 2bx divided by 4. Is this a linear function of b? No. I mean, it's extremely nonlinear. So against our intuition, even if, you know, B appears as an affine translation, the translation operator in the space of function is extremely nonlinear. So Wiener, with this theorem that we now lost, let me see if we can find it again, inaugurated, what is this? Information theory. It took 57 years until Cybenko proved the next theorem on this that was actually published in a control journal, Mathematics of Control Signals and Systems, where Cybenko said, listen, I can do what Wiener did, but now, instead of the Gaussian, I can take a sigmoid function. Why this was another article? Well, because the sigmoid function does not fulfill the condition of Wiener that the Fourier transform is positive. So think that the sigmoid function is very close to the jump function, the Heaviside function, whose Fourier transform is the Shannon function, is sin x divided by x. So it's something very oscillatory. You can compute it if you wish. As an exercise, check what is the Fourier transform of a sigmoid function. Sigmoid function is just a monotonic smooth function that has 0 limit here and 1 limit here. You can write it explicitly, just an exponential expression, or the arctangent function. You can think of many sigmoid functions. But I mean, this was an important result because the sigmoid function now you see is 0 to the left, 1 to the right. It represents well the functioning of the neurons we wanted to mimic in the neural network, on and off and on. But Wiener didn't apply. So it's because of that that Cybenko was obliged to enrich the original ansatz by Wiener, not only replacing the Gaussian by the sigmoid, but actually employing one extra parameter. And the parameter now is scaling. So it's not only now, so Wiener did translations and amplitude, and then what Cybenko did was translations, scaling, and amplitude. Okay, very good. We continue tomorrow. Thank you for your attention.